So we switch the gears now, and we go from quantum optics or superconducting quantum optics or microwave quantum optics, which we had before, to the topic of the superconductivity, and one of the really hot topic which generated a lot of research in the last years. And Sergey actually contributed to this a lot. So he did his studies in the Moscow University of Physics and Technology, and also did his, I think, master also in Chernogolovka in the group of Valery Ryazanov. Then he went to the US, to the group of Dale van Harlingen, and did his PhD there at University of Illinois, 2005. And then I went to work to Delft in the group of Leo Kouwenhoven, participated exciting first works on the Majorana fermions, observing Majorana fermions in nanowires. And then 2012, he started his own group at University of Pittsburgh, where he is located now. And I think this field really became very hot in the last couple of months, so to say. And one of the contributors to this hotness is Sergey himself. So I'm really excited to hear his lecture today in the school. And it's really something from the front of the research and discussions around the world. So thanks for joining us, and we're looking forward to your talk, to your lecture.
Yeah, thank you, Alexei, very much. And yeah, thanks everyone for connecting. I can sympathize that you are overloaded by now mentally with all the great science that you've been hearing. And I'm sorry to be the one to pile another hour and a half on top of what you've already been learning. Yeah, totally. If you want to take a break, do it at any time. Also, we can keep it perhaps lively. And if you like to interrupt me or ask a question in the chat, I'm going to have a window open here, and I'm going to react to what you ask, or raise your hand in Zoom. We can do that so that I adjust my explanations based on what you would like to hear or repeat it, right? So it's all for you, right? I'm here for you, so just ask your questions, and I'll try to help. Right. So as Alexei said, I've been at it for about 10 years. This subject is frequently mentioned in the context of quantum information, and I will motivate where that comes about. It's also a lot of interesting physics, just even if it has no applications in the end. And it is intimately related to superconductivity. Actually, what we're trying to discover is a new type of superconductivity called topological superconductivity. And interestingly, yesterday I had the privilege to lead or chair a discussion. So it wasn't talks, it was a discussion on the subject of topological superconductivity. And there were some very high level, very impressive people in condensed matter physics present. And I ran a Zoom poll where I asked one question: has topological superconductivity been discovered? And the answers were yes and no. So the answers were 76% no and 24% yes. So this is just to give you a feeling that what I'm talking about is best described as work in progress, though a lot of papers have already been published with pretty big claims. Okay, so after this slow ramp in, let's do an introduction. And the introduction will also be pretty basic. I'm an experimental physicist, and I don't do much equations and stuff like that, Hamiltonians, but I will have a little bit. So the story of this physics dates pretty far back to the foundations of quantum mechanics. Ettore Majorana was a sort of under-recognized genius of the era. Partly perhaps because he disappeared mysteriously in 1938. And he was working on solving the Dirac equation, which is a relativistic equation for the electron. And he found some solutions, which can call real solutions. Real in a sense that they have no imaginary part, expressed by this equation on the screen, where the object, the solution is self-conjugate. Of course, these are quantum operators, so they're not complex numbers, but the intuition from complex numbers applies. So these are real solutions of Dirac equation, and the interpretation, every solution of Dirac equation is a particle. And so if it's a self-conjugate like this, then it's its own antiparticle. And this is unusual for fermions to be their own antiparticles. It's paradoxical, and this is captured by these pictures on the screen, like a tennis ball that makes one with its own reflection, or René Magritte painting where reflection is the same as the object that reflects in the mirror. Now, we are studying this in a condensed matter physics context in materials. So we are after emergent excitations of electrons in condensed matter systems. And so in condensed matter systems, we also have Dirac equations. For instance, in graphene or topological insulators, we have Dirac cones, which is a spectrum of Dirac equation. We have matter and antimatter, electrons and holes. And we also have particles that are their own antiparticles. For instance, at the symmetry point of this spectrum, at the Dirac point, for those of you who know graphene, we would have, it will be unclear whether we have a particle or an antiparticle. So we are looking for equal superpositions of electron-like and hole-like quasi-particles. This is different than exciton. Exciton is one electron and one hole from two different bands in a semiconductor. And this particle is one particle, which is a superposition of two. So such superpositions are also known as Bugaloop of quasi-particles. Electrons here are excitation slightly above Fermi level in a metal, and holes are slightly below, empty spaces slightly below. So superpositions like this are known as Bugaloop of quasi-particles, which tells you that to look for such things, you want to go to superconductors. But in conventional superconductors, such superpositions are unstable. And so we need to do something extra to the superconductor. But first, let's play a little bit more with this Majorana fermion math. So I told you that they are real solutions of a Dirac equation, and that's unusual because the most common solution of Dirac equation is then complex. And then we call them complex fermions, although actually they are better known as electrons or holes. Those are actually complex fermions. So I denote them with C's, C dagger and C. C dagger is never the same as C generally, but you can express a complex number as a sum of two real numbers, right? So there is a transformation on the screen from the C basis to the gamma basis. Now, there's a purely mathematical artificial transformation, which tells you, however, that in principle, you can think of any electron as two Majoranas flying together in space. And so it's depicted here on the screen as a rectangular box would be an electron or a hole. And inside of it, the two stars are the two Majoranas flying together. And so most, 99 million cases out of 100 million, they are inseparable. But an interesting objective is to separate them and get a hold of one of the stars like this, right? So have them split like this. So that's the goal of our research. And well, it is actually on a pretty firm theoretical footing that this is possible. It's possible to take one electron and split it into Majorana fermions and spatially separate them. And this dates back to Alexei Kitav. who put forward a what we call a toy model. Toy model because it's actually very simple to solve, a beautiful, like a two-line calculation to see the majoranas from this model. But it is impossible because these C's and C daggers in his Hamiltonian are spinless fermions. And in real materials, we have always spinful fermions. They are spin 1/2 particles or 3/2 or something like that. And so that creates a problem for majoranas. I'll show you later. So then from the toy model, another 10 years of development took us into the realm of real materials that exist. The first work was Fu and Kane in 2008, which figured out how to map Kitav Hamiltonian onto existing materials, so topological insulators. They were still pretty novel at the time, but at least they existed. Then 2 years later, these two physical review letters papers mapped their Hamiltonian is a map from the Kitav Hamiltonian onto very, very conventional materials that existed for decades, semiconductors and superconductors, just conventional superconductors. And that at that point, we kicked into gear and we began trying to build this thing because we had these materials in the lab. So there were also many other ideas that I will touch upon, but these are the ones relevant for my lecture. Here is a cartoon representation of the Kitav model. Like I said, it's a two-line calculation, but I still prefer to show with pictures. So remember, single fermion C is 2 majoranas, 2 stars. And now what Kitav did is he constructed a one-dimensional chain of these complex fermions C and written out all the stars in the chain. Then what he realized that if you add superconductivity to the chain, then the sides of the chain get coupled and new objects get created out of adjacent sites. And what's interesting is that you still have a chain of fermions. These dashed boxes are complex fermions, but the boundaries of the boxes have shifted by 1/2 of the period. And as a result, there's one unpaired star on the one end and one unpaired star on the other end. And this is the idea, to break one electron into 2 unpaired stars. Now, why does it not work with spinful? With spinful fermions that we typically have in our materials, spin 1/2, we just have to write down 2 copies of this model, and each copy will give a star at the end, but you can see the stars at the end can hybridize, and there isn't a single unpaired non-trivial majorana on the end. There is just another complex fermion at the end. And so this does not work. We really need spinless fermions. Okay, so what's the big deal? Why are we trying to chase after this idea put forward by an obscure genius from 1930s? Well, that's because we don't really go after what he did. We think that in condensed matter, these Majorana fermions are a whole lot more unusual and exciting than what Majorana himself derived in 1930s. And it's because they are expected to be nanobillion. They're nanobillion particles. Nanobillion particles have not been demonstrated in any shape or form convincingly. And they are technically their own class of particles, like fermions, like bosons. So Majorana fermions, actually not fermions, they're nanobillion anyons. And that's because they have a different set of exchange rules. So, you know, for fermions, if you swap 2 fermions, you multiply wave function by -1. If you swap bosons, nothing happens, just multiply it by 1. If you swap nanobillion anyons, you have to follow these rules that you see on the screen for swapping nanobillion anyons. So let's follow this through. let's say we have gamma 1 and gamma 2 here, and we move them like this. So gamma 1 becomes gamma 2. Gamma 2 becomes minus gamma 1. So if the superposition of 2 was an electron, a C dagger, then the superposition of 2 upon exchange became a hole. So we replaced an electron with a hole by just moving things around. That goes against the principle of particle indistinguishability that we all learned from college. And that's very interesting. Another important thing that I have to clarify, since this is a lecture, is that we often use the language of particles. We say Majorana particles, nanobillion particles. And so what that creates in your head is that you have particles sitting around in your crystal and you may be manipulating them. It's not quite true. Majoranas are like modes, like energy levels in a particle in a box potential, like energy levels in a harmonic oscillator, like energy levels in an atom or a quantum dot. They can be empty or full. So there's two possibilities for this mode. It can either hold an electron or it can hold a hole. Okay, and that can be done by adding charges to it. You can just dump charges to it and you can change the occupation. So for instance, you can pass current through Majorana and the occupation will change from electron to hole, electron to hole, electron to hole as you pass current through it. And so this Majorana is not really a particle, it's kind of an energy level. It's a space that you can occupy. And so if you want to define a qubit, as you've been hearing about qubits a lot, I believe, if you want to define qubit based on this, it is a two-level system, electron or a hole, and therefore you just define qubit based on the occupation of this Majorana mode, of this Majorana energy level. Now, so one of the goals is to perform this exchange of Majoranas, but I told you that they, at least in Kitav's proposal, they are on the ends of a nanowire. And so that creates a logistical problem. If you move them along the nanowire, they will overlap at some point. They will be in the same spot. And at that point, they can annihilate. Particle and antiparticle annihilate. So they overlap and they split, hybridize, and the quantum information can be projected at that point. So we don't want that. So people came up with a solution that we need a network like this. They call it Tjunction. And in a Tjunction, we can braid them by moving them sequentially like this so that they never run into each other. So that's how braiding would work when we get to it. Now, moving the object along the wire is also very hard. So instead, another approach people came up with is put an auxiliary Majorana in the middle, the blue one, and then couple and decouple Majoranas to it from the different branches, like yellow to blue to green, blue to green, green to blue to red, and then red to blue to yellow. Couple them all together so nothing moves. You just change their overlaps. And this way you move the information around this T-junction and you manipulate the qubit this way. So the reason I'm showing you these is to impress upon you that if we are to build a qubit out of this, this would require a pretty extraordinary new development of just hardware. How to manipulate these things would look very different. Also, how to read them out. I mentioned that if you merge them, they annihilate. This is conveniently a readout mechanism for this qubit. So you move them together and it projects either onto electron or a hole. You read out what's in that pair. And so you need some kind of a charge readout, or you can couple it to another qubit for readout. Another thing you may be wondering about, where does this charge come from? right? It's kind of magical that we move things around and an electron appears. In reality, physics prohibits this. There is charge conservation, and none of this goes against the fundamental laws of physics. So the answer is, well, that extra electron comes from somewhere. And to define where it comes from, we can think of a system of not 2 Majorana, but 4. So then when we do a manipulation and we draw a charge, it can come from the 2 auxiliary Majoranas. And then it comes onto these Majoranas, and then we do another manipulation and it goes back. So a qubit requires at the minimum 4 Majoranas, and in practice, even more for braiding and readout and so on. So it is not like you have 1 Majorana and it's 1 qubit. 1 qubit can be 4, 6, 12 Majoranas and so on. So quite a large overhead. So this is a picture from Physics World from a few years ago of how this quantum computing is supposed to work. You have a plane, a sheet, where these Majorana modes are located, and you move them around. So vertical axis is time. You move them around, and as you make knots, it's called braiding in the theory of topology. As you braid the world lines of these defects, these modes, you perform computation. And so why people bother with this? Well, because of this noise. So you see noise is represented as wiggling in the world lines. And as long as the world lines don't cross each other due to this noise, information is not changed. So it has certain robustness to certain kinds of noise. And that's why people are interested in this approach for quantum computing. My own personal view, as I already mentioned in the beginning, is that the fundamental physics of it is by itself so interesting. You can discover a new class of particles by working on this. You can discover a new type of superconductivity that carries these particles, the spinless superconductivity or topological superconductivity, that it's worth the effort. And if quantum computing can benefit from it sometime down the road, great, win-win. So it is a major undertaking. You know that you see that I outlined. You have to control numerous Majorana modes in space, then read out with other qubits. So to perform this experiment, you have to kind of build a small quantum computer just to verify that you have done this braiding. And so you need a collaboration of many research groups. I certainly would like to be one of these groups. And so this remains a wonderful physics opportunity. You have to think of it as a big experiment, like CERN or telescopes and things like that. Now, I mentioned that there's a large number of platforms onto which the Kitav Hamiltonian has been mapped. The toy model has been mapped onto many different materials. And they form this cloud, this primordial soup of ideas, which is fun because you can think about very different materials. You have spin liquids and helium, superfluid helium-3, could be Majoranas there, topological materials, and so on. Still, the poll of the experts in condensed matter physics shows that it has not been discovered. 76% to 24%, I told you from yesterday, recent data. So there is no clear leader. How are we going to get there? There are some platforms that have been researched more than others, like nanowires that I will talk about. But it's too early to say which platform will get us there. So what I use is these 4 questions. If you want to assess any of these platforms, if you run into some Majorana research online or hear a talk, you can ask these questions. First of all, is the theoretical proposal itself even reasonable? Is it a stretch that in this material, this phase can be realized? Are there too many assumptions and wishful thinking? Is it verifiable? Is there a method with which you can measure an experimental technique like tunneling that will tell you that majoranas are there? Now, is it braidable? Meaning, can we find a mechanism to perform these manipulations, couple and decouple majoranas or move them around? And finally, if you want to build a quantum computer out of this, you have to think about scalability. So for instance, semiconductors naively offer a lot of opportunities for scaling because we have done that in classical computing. So maybe that's a promising avenue from that point of view. Now, let me talk about the approach I've been focusing on for the last 10 years. Let me tell you how we take Kitav's idea and map it onto this system, which is a semiconductor nanowire. So first of all, it's a one-dimensional quantum wire, which is what Kitav wants, a one-dimensional system. Then it has spin orbit. I'll tell you why in a second. But basically, the spectrum of a one-dimensional quantum wire is a parabola. It's a p squared over 2m dispersion in energy. And a spin orbit interaction splits the two parabolas in spin. So the left one is a spin up and the right one is a spin down. And superconductivity opens these gaps here around zero energy. That's what superconductivity does, creates a gap in a single particle spectrum. And then magnetic field closes this gap and then reopens it. So we are always in a superconducting state, but when the gap closes and reopens, we enter into a new quantum phase. There is a quantum phase transition into the topological phase. Now, let me motivate to you what all this means. So, one-dimensional wire with superconductivity, we know those are required by Kitav. Why do we need magnetic field? That's our way to make it spinless. So Kitav wants us to have a spinless system. We cannot have a spinless system, but we can have a spin polarized system so that one of the spin components is very far in energy and we don't have to worry about it. So we have a spin polarized system. Now, this creates a problem because we want a spin polarized system that is superconducting. That's a problem because superconductivity of the conventional kind is a spin singlet pairing of electrons. So all electrons are in singlet states, but magnetic field wants them all to be aligned, so like a triplet. So normally magnetic field suppresses superconductivity, it destroys it. So we needed to survive. So that's why we add the spin orbit interaction, because spin orbit interaction mixes spin up and spin down states with the orbital states. So it mixes singlet and triplet and allows superconductivity to survive at high magnetic field and carry it into this topological regime. Basically, what we need is we look at this gap here at zero magnetic field, and we need to apply enough magnetic field, but the Zeeman energy closes this gap. So G mu B equal to this energy gap delta. And then beyond that, we enter the new phase. So here is what happens in greater detail. And it's a little bit of a tutorial also in how to think about Bugaloop transformation. So you can move along this graph in many different directions, but you want to start from A and you want to end at I in the bottom. And so what we have here is first row, the top row is single particle electron spectrum, whereas second row, the middle row, shows you the Bugaloop representation, but without superconductivity. And then the bottom row adds superconductivity. Now, columns are like this. Left column is zero magnetic field, zero spin orbit. Middle column is spin orbit, and the right column is magnetic field, right? So we have all combinations of ingredients here on the screen. So for instance, we go through the top row, panel A, I already talked about it. It's a doubly degenerate, spin degenerate, single quantum wire spectrum. There is a parameter KSO, and the two parabolas shift like this for spin up and spin down. Now we apply magnetic field, external magnetic field. And what it does is it takes this point where spin orbit is inactive, and it makes a Zeeman splitting here. So here there's no spin orbit because it's proportional to momentum. So spin orbit is 0 here. So now we have a gap. Okay, so the middle row is the same stuff, but what we did, you can see that this parabola is now inverted like this. That's because when we do the Bugaloop of transformation, we say that for each particle, there is an antiparticle at the same energy. So we double the number of states. We have electrons and holes, and so the electron spectrum now looks like this because there's a parabola facing down, which is made of holes. Right? So we symmetrize and double the spectrum. That's the Bugaloop of transformation. And now the bottom column is we just open a bunch of gaps. So we can open a gap at 0 field and with no spin orbit, and it will look like this. This is what superconductivity does. We can open it with spin orbit. Then we have 3 gaps, one at 0 field, one at finite momentum, at Fermi momentum. And now, when we add all of it together, spin orbit, Zeeman, and superconductivity, we have 2 different magnitudes of gap generically, because you see the gap at 0 momentum, right? This gap at 0 momentum, E gap 1, it can be opened 2 different ways. Look at panel C. It can be opened by Zeeman splitting, and look at panel H. It can be opened by spin orbit. Okay, so there's 2 different mechanisms to open this gap, and it turns out that they compete. So if one opens, the other one wants to close. And so which one wins determines if you have trivial superconductivity or topological superconductivity. So if Zeeman energy wins, you have a topological superconductivity. So here on the screen, I have more of the spectra as a function of magnetic field. So on the left, we have magnetic field EZ, Zeeman energy, less than delta, less than the induced gap. And we have a fully gapped spectrum, nothing at Fermi level, nothing at 0 energy. Then there is a critical point, which is a quantum phase transition point, at which Zeeman energy is equal to the gap. And at this point, we have the middle gap at k equals 0 completely closed. Okay. Now, when we go beyond, when Zeeman energy greater than the superconducting gap, again, we have all the gaps open, but the middle gap is kind of inverted. And so you cannot normally see that. You cannot see whether the gap is, let's say, positive or negative, whether you are on the left or whether you are on the right. The only way to see that is to detect these extra states that are created. So these are Majorana states, right? At the phase transition point, by the way, we have a kind of a Majorana mode running through the entire nanowire. And beyond the phase transition, we have these localized Majorana states at the left and the right end. So you cannot see them in the spectra in the bottom because this is for infinite wire, a wire that has no end. So in a wire that has no end, there is no extra state at 0 energy. This state is only created when there is a transition from a trivial vacuum state to the topological state. At the transition point, there will be an extra state. This is similar to other topological phenomena like quantum Hall effect, where the edge state runs along the boundary of the system with a vacuum, or a topological insulator where the same thing happens. So there needs to be a boundary from trivial to topological creates a state. Okay. Now, let me see the time. Okay, we are moving pretty slowly here. Okay, so an important concept, some of you maybe know, but an important concept for both creating these states in a semiconductor and for detecting them is Andreev reflection. So we will talk about this. I'll show you some measurements where it plays a role. It's a beautiful effect, which explains how a single electron can enter a superconductor where there is a gap and there is no possibility for it to exist. So it can do that through Andreev reflection. Rather, electron is reflected as a whole, but a current can still be carried. So the way it works is an electron hits the superconductor, a hole comes out in the opposite direction, and by charge conservation, a Cooper pair, two electrons in a singlet state, are created in the superconductor. This can also work in the reverse. You can send a Cooper pair out and it will go through this Andreev cycle. This will come up a lot in the lecture, so I put a slide on this. Any questions so far? This has been the conceptual part of the talk. Now I will start showing some experiments and stuff. Okay. Well, at any moment, just drop the questions in the chat. No problem. Right. So how do we detect this stuff? Well, we do the basic measurement of all physics. We apply voltage and measure current. It's called transport, or in this case, tunneling, because there is a tunnel barrier here. So we have 4 ingredients in our recipe, and they are the nanowire with spin orbit, and there is magnetic field on, and the superconductor is just physically put on top of the wire, and it induces, by Andreev reflection, superconducting correlations between those electrons and holes in a non-superconducting material, which is a nanowire. And so the entire topological physics takes place next to a superconductor in the induced superconductivity regime, which is labeled topological superconductor on the screen. And on the ends of that regime, they're expected to be these Majorana zero modes, uncoupled, and they manifest as states at zero energy, which means at Fermi level, or which means at zero source drain bias in this experiment. So if this voltage here is 0 on the battery, we should hit that level. And the way we detect it is there is a little bit extra conductance, a little more current can pass per delta voltage at zero bias. So it looks like a zero bias peak that you see here in our original data, or in this newer data. Here is a zero bias peak. Now let's talk a little bit about these data, how they're measured. So you set up this device, you measure current here, and what you plot is DI/dV, so conductance or differential conductance, which can have a peak at 0 voltage. So at 0 magnetic field, we are missing one ingredient. Remember, we need Zeeman splitting. So what we have is this kind of spectrum with 2 peaks at finite bias and a suppression in the middle. So this is just a manifestation of the induced superconducting gap, where some states are expelled from the middle and piled up on the sides. So these kind of features are well known. BCS peaks, they're called. They're superconducting quasi-particle peaks. Then when we apply magnetic field, all these curves are offset for clarity. After about 100 millitesla, which is quite a significant magnetic field, we start seeing this zero bias peak, and it persists at zero bias, doesn't move from zero bias for a significant range, as expected from a spinless state. It is not sensitive to Zeeman splitting, right? It doesn't Zeeman split. So here is the same in color. I will be showing some color plots. So I want to introduce them here. Color is conductance. dark blue is low conductance, and red is high conductance. So these two features at finite bias are the superconducting peaks. And then zero bias is this streak, zero bias peak is this streak. And again, it stays pretty fixed to zero bias. Now, to give you a sense for energy scales here, what these millivolts mean. So this is a 700 microvolts. The G factor of electrons in this material, this nanowire, is indium antimonide, is very large. It's 50. For free electron, it's 2. So we have a lot of Zeeman energy per magnetic field. So for 1 Tesla of magnetic field, from 1 to 2, for instance, it is equivalent to Zeeman splitting of 1.5 milli electron volts. And 1.5 milli electron volts is this entire range here. So if we had a state that had spin, it would move across this entire graph in just this one interval from 1 to 2 Tesla. Right? So the zero bias peak stays, from this point of view, impressively pinned to zero bias. And that is why, that is the reason we investigate it as Majorana. Now, as Alexei mentioned, in the beginning, the field is hot, and he meant probably in not a very positive sense. There is a lot of controversy right now. And this is related to the fact that a lot of Majorana claims have been made about the zero bias peak, but some of them are for sure not correct. And maybe all of them so far have not been correct. So what is the issue? Well, there are other possibilities to get such a zero bias peak. The one we want is this one on top, where the green wave function and the red wave function are the two Majoranas. Now I show them as a spatially envelope wave functions that have certain dimension along the nanowire. And we want them separated, right? As Kitav wanted us to have them unpaired, and that's what we are after. Well, another possibility is that due to some factors like short nanowire or disorder, the two wave functions are not very well separated, like the middle picture. They are just partially separated. So that is still derived from the same physics, perhaps, but it is not useful for quantum computing anymore, for sure. But what's more, the same zero bias peaks have been found in completely trivial Andreev bound states. So electrons living next to the superconductor in the nanowire, stage generated by constant Andreev reflection from the superconductor, completely trivial, which I mean that the red and the green wave functions, the two Majoranas that make an electron, remember each electron can be two Majoranas mathematically, but the two components are completely overlapping. And it's like the two Majoranas are always flying together in this electron, never separate, still can have a similar zero bias peak. Okay, so that's a methodological challenge that we had to overcome. And well, the good news is we overcame it in the sense that we can tell Majorana from Andreev. The bad news is everything we see is Andreev for now. Now, what are these Andreev states? I already motivated to you what Andreev reflection is, right? It's some kind of an interaction of non-superconducting electrons as they try to interact with a superconductor. So another way to think about Andreev reflection is if you have a single site, a quantum dot, a single site, one energy level, right next to the superconductor, right? This is conceptually similar to having a Majorana there, right? I told you Majorana is an energy level. So this one is just an energy level, doesn't have to be Majorana topological, just an energy level coupled to the superconducting lead. So this is known widely as an Anderson impurity model. And it's been, you can solve it analytically, I believe, but people have also done numerical calculations, things like that. And so what this model produces is in the spectrum of the system where you have a gap. So this is a superconductor, has a gap. And on the on the dot, on the energy side, you have some levels, but this interaction generates additional levels inside the gap. So energy levels of the dot get pulled into the gap and create these particle hole symmetric levels due to superconductivity, which are denoted by these red letters, whatever they are. I forgot what these letters are called. Anybody remember what this is called? Let's call it chi. Right, so by coupling a normal dot with a spin to a superconductor, we get these extra states. And oh, zeta, thank you. That rings a bell. That rings a bell. Right, so by coupling superconductor to this dot, we get extra states. And if we ask ourselves what is the ground state of this system, then we have to look at this phase diagram. Where doublet means that we just have a spin, either up or down. So there's the ground state is doubly degenerate. There's two states. And the singlet means that, well, there is a singlet state formed. It's a many-body singlet because, say, we only put one particle on this dot. How can we have a singlet? It is hybridized with some spins in the superconductor. So it's a many-body BCS singlet. That's what it's called. And you can see how it comes about. So the vertical axis is the coupling parameter. So if the coupling parameter is 0, we just go from 2 particles, singlet, 1 particle, doublet, no particles again, singlet, or holes. And then as we couple more and more, if we couple very strongly, then electrons in a superconductor screen the spin on the dot and make a many-body singlet ground state. Right. So then when the doublet is the ground state, then we add another electron to the dot. Then singlet is the excited state, the state of 2 electrons. And when we do transport measurements, we send current through the dot. And so what we do is we go from n to n plus 1 electrons constantly, n to n plus 1. So we have a transport resonance whenever our voltage bias matches this energy difference, which is equal to zeta. So this allows us to map out the spectrum of Andreev states by passing current. Voltage will just give us the energy of Andreev states. And also you can see from this that when we follow this line here, is topological phase transition, quantum phase transition line, then the energy difference between doublet and singlet is 0. So the energy difference between these blue lines is 0, and we will have a 0 bias peak in our spectrum. So this is how it looks. Again, this is a phase diagram, and this is actual data from my lab. These spectra are Andreev spectra, and so you can see at 0 magnetic field, as a function of gate, we have these states that never reach 0. That's because we're here in a singlet ground state regime. So when we change the charge occupation of the dot, we always stay in singlet. We are here at strong coupling. Well, there is another possibility for what can happen is if we apply magnetic field, then the singlet, then the doublet state, Zeeman splits, and the energy difference between singlet and doublet starts to go down. So we can have a quantum phase transition as a function of field. And this is what happens here. At this field, singlet and doublet energy is 0, and we have a 0 bias peak just at this field. Because if we keep going, it splits into loops and it evolves. So generically, what we have then as a function of magnetic field is this resonance. Zeeman splits, one of the branches goes down, one goes up and above the gap. And there is a point at which we have a 0 bias peak. Now, this 0 bias peak is quite different from Majorana because it's intermittent. It's just from a crossing of 2 levels. It's momentary. It is not stuck for a long time at 0 bias. Except look at this gate voltage of 0.76 volts for this quantum dot. You can see that for whatever reason, some uncontrolled parameters, the 0 bias peak forms here from the crossing of 2 levels, but they never split. It just keeps staying here and stays for a considerable energy of half a Tesla which is about a millivolt of energy, just doesn't split, right? And so if you find this in your data, you don't know much about Andreev states, you can say, well, maybe this is Majorana, right?
What in general makes the picture slightly asymmetric with respect to the zero line?
Yes. So it is largely symmetric, I would say, but yes, there are some asymmetries. So there are several components to understand asymmetry. First of all, of course, in superconductivity, we have this emergent particle-hole symmetry. It is emergent, so in principle, it doesn't have to be exact. And especially when the Fermi level is not orders of magnitude larger than the single particle energy, it's possible, but we don't think that's what's happening here. There are two classes of explanation. One is just kind of a decoherence. When you tunnel, if your particle that you tunnel with is more electron-like than hole-like, then it will pick up the electron part of the Andreev state, and it will couple less to the hole part. And so that particle-hole symmetry will be violated. This also happens often at high tunnel barrier heights when the particle has a lot of time to collapse onto being electron or hole, let's say, before entering. Another class of explanation is just mesoscopics. As you change parameters, gates and fields, there are resonances that cross through, and they cross with some slope. For instance, it could be a slope in magnetic field. And so if there is a slope, it can create at any given cut an asymmetry, right? Because it already reached the top part, but it hasn't reached the bottom part yet. Mm-hmm. So there's kind of a lot of different possibilities for asymmetry. Generically, similar explanations are given by STM people when they're asked about asymmetries in their tunneling spectra, right? This is also a tunneling experiment, just like what they do.
Okay, thanks.
Right, so to illustrate my point that I'm not just, stoking paranoia here about the similarities here. So here's real papers. One on the left is a little bit earlier, before a lot of studies on Andreev have been done. And here we have, again, inside this induced gap, this Andreev resonance here. Sorry, Majorana. It was called Majorana in this paper. So this paper interprets it as Majorana. Here, pretty similar looking stuff. Again, two resonances merge, and a zero bias peak here is this bright volcano in the middle. Again, existing for a pretty long range of field. And this is 100% not Majorana, it's Andreev, because these people in 2014, they made a little quantum dot next to the superconductor, and they studied states inside that tiny dot. So there is no room to separate the two wave functions. It's not possible, okay? By the way, here, if you look at the magnetic field range, it is not very impressive. This is probably just data that's been stretched to look like an extended zero bias peak. It is probably just a crossing of two states. Okay. So we have this issue. We have one effect and two explanations. So why would Andreev states stick to zero bias like this? We identified 4 possibilities. Okay, the first one is actually, for completeness, I put Majorana here. Majorana can look like this. Doesn't even need to look like zero bias peak. What you have here on the screen is this thick blue line is the superconducting gap in the parent superconductor, the niobium aluminum that you put on top of the wire. And with magnetic field, it closes eventually. So hopefully you have enough range to study something interesting within. So when the parent superconductor dies, it's game over, right? There's no superconductivity anywhere. So inside this induced gap, we have all kinds of states. So this will be the closing of the induced gap, marked in pink is the closing of the induced gap, and then reopening of the induced gap leaves behind two intertwining resonances, which are Majorana states. And the reason why they overlap and come back together is because of the finite size of the system, and the wave functions overlap a little bit. So there is hybridization, exchange effect, like in atoms, like a molecule, the Majorana molecule. They're partially fused. That's another way to say it. So these are called Majorana oscillations. So that's even possible. That can still be Majorana. Well, here is another possibility where these are just Andreev states. They come down, these resonances come down to zero bias, and they stay. Why is that? That's because the gap is closing, the parent gap is closing, and these states above the gap, they push on the Andreev states below the gap. So they exist in the same space, they hybridize, they overlap, and they anticross. So the top states push down and the bottom states push up. So the subgap resonances are squeezed to zero and create this extended presence. Another possibility, also based on anti-crossing, so it's lower left, but these are anti-crossings between the subgap states. So let's allow three subgap states, three Andreev states below the gap, red, green, and pink. And they can all interact due to spin orbit or other effects. They come together, they overlap, and they anti-cross. So the bottom one is pushed further down to zero from both sides, right? Due to particle hole symmetry of the spectrum, it's pushed down and up, and it creates this zero bias peak. And some of these may be invisible, right? Here I'm start to sound paranoid, but if you tweak the color scale of these color plots, you may see some faintly visible resonances that may be pushing down the zero bias peak. Finally, this last one is kind of a disorder explanation. And by the way, all of these we observed. So here we have, think of, let's say, 3 quantum dots next to the end of the nanowire. Not one dot, but 3. And each has Andreev state that comes to zero bias at slightly different field. And so it creates this extended presence, right? First one comes and another comes and another comes, and there's always a zero bias peak. And these lead branches might be fainter than the central ones because there is an extra resonance from bottom and top here. So that can be another possibility. Okay. So this is the problem of the moment for an experimental physicist, how to tell Majorana from all this other stuff. Well, some people say it's impossible, or we need to do more advanced measurements like braiding. But I say, stay the course, just do careful work, analyzing all the parameters of the system, and you will be able to tell if you have one of the 3 or if you have Majorana. That's because the beauty of this semiconductor nanowire approach is that there is a lot of control knobs. There is magnetic field, which we can turn on and off. We can rotate the field. We also have gate voltages on electrodes underneath the wire, tunnel electrodes, all kinds of things. And if a state is Majorana, it would behave consistently no matter how you cross and slice the parameter control knob space. Right? There is a simple theory that predicts the behaviors of Majorana, and we should just explore if the hypothesis holds consistently in the same nanowire. And these are the 5 things that I put forward as not the ultimate, but the simplest to demonstrate set of requirements before it can be considered Majorana. So the first one we already talked about. It's the sticky zero bias peak, meaning that it's not just a crossing of resonances like Andreev states, but it actually wants to stay at 0, right? And also I showed you that this is not sufficient, definitely. So we want to look for more things. So another thing that is easy to look for, because now we have vector magnets, we can rotate fields like that. We can see if spin-orbit interaction plays a role here. So spin-orbit interaction is inherently anisotropic. It couples certain momentum direction to spin, and so it can be thought of as a field in a certain direction. So if we cancel that field, we can cancel the spin orbit effect. So we find the direction of spin orbit field, and the zero bias peak should disappear. Right? The third one is along the lines that I said. We have different control knobs. Magnetic field and electric field are gate voltage and Zeeman splitting. And in that space, it's a topological phase. It's a quantum phase transition that takes us there. And so it should occupy a certain area in this phase diagram where we have zero bias peaks, right? It shouldn't be an accidental point that we fine tune to. Only for one gate voltage, we have a peak, or only for one field. But it is a kind of a robust area. So if we find it, and if we can compare it to theory, that's a pretty strong indication that we are on the right track. Now, peak oscillations, we already talked about. If we couple and decouple Majorana. So because we have all these gates and fields, we can change the shape of the wave function. For instance, you may know that at a phase transition, the coherence length is infinite. I already told you that at the phase transition point, you have kind of a Majorana mode running through the whole system. You can think of it as Majoranas of infinite size. So we certainly have a strong overlap of Majoranas at the phase transition point. So if we go near this regime, near the phase transition, we should have these Majorana oscillations as a function of gate or magnetic field. And this would be also proof that we are looking at the right thing. And finally, there should be two Majoranas. Remember, Kitav split an electron in the left part and the right part. So if we have a zero bias peak on one end of the wire, there should be another one on the right end. Okay, so the next question is, how are we doing with respect to these 5 criteria? So I put here all of the experiments done to date on this system, semiconductors and superconductors. And I put in the columns the 5 criteria I put forward. And the green means they have claimed to see it. So we see not so many green squares, right? In particular, nobody has demonstrated all 5, and certainly not on the same nanowire. But some have shown 2 or maybe 3. One interesting thing that you can see here is that the last column, the 2 end measurements, is empty. Nobody has found 2 Majoranas on the same end, right? So this leaves a possibility that you can fine-tune your data on one end to make it look Majoranish, but on the other end, it fails. So this, I guess, important message about how to take data carefully, look critically at your results. Right. So I'll show you what we found. We tried this experiment. It's a relatively straightforward extension of what I've been showing you so far. Here we have the same setup, a nanowire. Here's an indium antimonide nanowire coupled to a superconductor. That's the same as before. There's a tunnel probe, normal lead, and then there's another one. So it's a 3-terminal device. So we can look at 2 ends. The way we do it in practice is we just bias the middle lead and we split current between left and right. So we can look simultaneously at the left end and at the right end, what the current shows, right? So if there's 2 zero bias peaks at the same time, that's great. Well, there isn't. So generically, we can find zero bias peaks. We can find one on the left side. So for instance, on the left side, here's a zero bias peak. Here's a gap. A zero bias peak appears at finite field. It is kind of extended. Here it is, and it's even quantized. It's of the value 1 in the units of 2e²/h. That's one of the signatures that some people explored for Majorana. But now we look on the right end. At the same time, it's a dip. It's not a peak, it's a dip. Right? So in general, if we plot, here is a dip, right? So this is just a snapshot. We explored all gates and fields and tunnel barrier settings for this wire, trying to find a correlation, and we couldn't. So this is summarized by this plot on the right, there is even one point where zero bias peaks onset at the same time on the left and on the right, but it's intermittent and accidental, right? So you can even fine tune the two sides to have zero bias peaks together, but there's no evidence that they're linked. Right? They come from different states. Okay, so I've been doing a lot of thinking lately about how we do science, and one of the things that came out of it in the light of our revelations is this opinion article I wrote for APS, and I recommend that you read it. But one of the plots is on the screen here. It's very qualitative, but it's kind of like a phase diagram of interesting topological phases that we were chasing for the last 20, 30 years. And it's in the coordinates of disorder. So how much impurities you have in the sample, what's the mean free path, from nanometers to millimeters. So millimeters is an extremely clean crystal. Maybe it doesn't exist even, but nanometers is pretty common, just usual material. And there's the energy scale, the energy it takes to enter the topological phase, right? So for instance, you have to, if your energy scale is 0.1 milli-electron volt, like I put Majorana here, 0.1 milli-electron volt, it means you need to be, for instance, below 1 Kelvin to see anything, because 0.1 milli-electron volt is like 1 Kelvin in kBT units, right? So you're confined down here. So the higher the energy scale, the easier it is to see. And the lower the disorder, the easier it is to see, because disorder, it can also be translated into energy. So if your disorder is 0.1 milli-electron volts, it will be very difficult to see a phase which has 0.1 milli-electron volts energy. Right. So we find some states like integer quantum Hall effect that's been observed at room temperature to be a very robust topological phase that there is no controversy about, right? And some ones that, like these interacting topological superconductors, parafermions, it's beautiful physics that I would love to work on, and I know we can make some initial steps, but the energy scale is just so low and the devices are complex, and so disorder is pretty high because of fabrication challenges. So there is no hope that we will see anything like this in the near future. Now, majoranas are in this zone that they call the fog of hope. This is a very common phenomenon in science, in the social aspects of science, I guess, that we find ourselves in this fog of hope. We want to believe that we discovered something. We see the evidence, but it's foggy, right? It's a little bit not good. There could be another explanation, or disorder is just a little too high, right. So we call it promising maybe, but after a few papers, we drop the promising or signatures and we just start saying, yeah, we discovered it, right? We go into this runaway process. So it's important to be aware that you are in the fog of hope and your vision can be blurred, obscured. You should turn on the fog lights, like when you're driving in the car. So that's one aspect. The other aspect is, well, how do we get out of the fog of hope? Can we get out of the fog of hope? Well, so I propose that we use this diagram to see how we can get out of the fog of hope. We have to go in this direction. We want to be here. So there's two pathways, pretty much increase the energy or reduce disorder, or both. And both of them lie through materials engineering. Materials and fabrication. So my thesis is then that we have achieved methodological clarity on the quantum transport side, how to tell Majorana from non-Majorana. You have to do this experiment in a consistent way, and this will tell you if you have Majorana. Now we need to improve our samples even further, because these nanowires are already single crystal, beautiful, defect-free wires, but we need to do even better. So we have some ideas, and I'm not going to run through them in the interest of time. But yeah, we have some ideas to add a shell and to increase mobility and to vary material components of the system to nudge us out of the fog of hope region and then more into the clear, reduce the fog. So I have something to be proud of, something to present to you along these lines. For instance, we have this result that I'm very happy with, where it's the same nanowire. Do you hear a noise now? Or is my voice still clear?
No, it's clear.
Okay, great, because there's a lawnmower outside. Zoom works well, huh? Yeah, okay, so it's the same nanowire, right? But we varied the superconductor. We worked with aluminum, we worked with niobium, now we work with tin. Tin is a well-known material, of course, but never been used in this context. And it's a beautiful thin shell of tin. You can't even tell where it is. I have to draw this line for you to indicate where tin is. So it's very thin, like 7 nanometers of tin or 15 nanometers on this 100 nanometer nanowire. And it shows good results. It shows this very clear induced gap when we tunnel into this tin. This is a log scale, so suppression of conductance is 2 orders of magnitude, which is sort of state of the art. And this gap survives to pretty high fields. Here we have 4 Tesla before it closes. That's because the film is very thin, so it's important to have a thin film. And we also saw 2E tunneling in this tin, which is not been seen in anything but aluminum until we did this in tin, which is important for topological qubits. But maybe the most interesting thing we learned, the most positive thing we learned from this is that for a while people said that, look, to have clean data like this, you need a lattice match between the metal and the superconductor. The atoms have to go continuously, smoothly, without defects from one to the other. And pretty much we showed in this work that this is not the case. Tin is not lattice matched with indium antimonide in this form, this beta tin. It has grains that are oriented all different ways. So there is no epitaxy, it's called, in this material. But what we found important is that the interface between indium antimonide and tin needs to be cleaned very well and very gently. So we use this hydrogen cleaning to remove the interface oxide and deposit the superconductor. This is just to give you a flavor of the kind of tricks we are busy with. For the last few years, I have been a materials engineer, trying to play with these parameters with my collaborators who are crystal growers and experts in things like molecular beam epitaxy and X-ray diffraction and so on. Okay, so I'm about done. What I showed you in this lecture is that we don't have Majorana yet. We certainly don't have a Majorana quantum computer, but we do have quantum computers. Quantum computers already exist. They're based on other things, superconducting qubits, for instance. And IBM is kind enough that you can actually create an account, log in, and start using a quantum computer through the cloud. And maybe some of you have already done it or certainly heard about it. So we've been doing that due to COVID also, because we couldn't enter the lab for a while. But we also have friends at IBM. And when you have friends at IBM, they let you mess with the quantum computer. They let you kind of hack into it and make new gates and things like that. So this was a lot of fun. And actually, I wasn't as involved as I like in this, but it certainly sounded like a lot of fun for my postdoc. And so as a result of this activity, this paper came out, which I bring to your attention, where our friends in Pittsburgh and IBM have used an existing quantum computer to quantum simulate the braiding of Majorana fermions. Okay. They used a certain piece of math called the Jordan-Wigner transformation, which pretty much moves you between Kitav chain with these dots, Majoranas, gammas, and an Ising chain of spins with transverse coupling. Okay, so this is also a nice piece of math to follow if you don't know it. It's a nice transformation. It's very clear. But basically, a gamma operator is transformed into like a chain of sigma operators. And sigma operators are superconducting qubits. You can think of them as spin 1/2 particles. So the mapping is complete, and you can even encode a Tjunction. And here we were motivated by proposals from Gerrit Schoen and Alex Schneerman, and there were 3 people on that paper, maybe Machlin.
No, this was Hans Muy, I think.
Yeah, it was from Karlsruhe. Yeah, it was Gerrit Schoen and okay.
Initial paper was Machlin, who actually had lecture yesterday. Sergey Schneerman and Gerrit Schoen. This is the paper and 90s, you mean?
Yeah, so this is not exactly that, but some of the ideas overlap. So for instance, if you want to make one chain, that's easy. Just map it to qubits, but you need to come up with a way to engineer this Tjunction. So they had a certain coupler in their proposal. And in this case, it's all done by quantum gates. This
was a recent paper with Hans Muy. Those two and Hans Muy.
Yeah, Hans Muy
like
was
3 or 4 years ago. Yeah,
Hans Muy was on it. Yes.
Yeah.
Yes. Yeah, and that's why it was all based on flux qubits, right? And there was a special qubit to couple 3 segments, and we don't have a special qubit. We just have whatever IBM didn't make a special chip for us just for this toy experiment. Okay, so this coupling is done also by gates. Right, so IBM machine is noisy, right? We're in noisy quantum era right now. So the error rate on a 2-qubit gate is 1%, which means that you cannot have more than about 25 qubit gates, 2-qubit gates, before the whole thing is just gives you a random outcome. So you lose any computational power. And you can see here from this braiding requires a lot of 2-qubit gates. So they went in and they did basically pulse engineering on the IBM machine, and they introduced the new gates. They used some tricks from NMR where you basically catch a spin as it rotates at the right moments for this algorithm. And they could extend the efficiency of the IBM machine and perform this full braiding. So they decompose the continuous process of coupling and decoupling Majoranas in 6 steps into these very small time steps. So that's called Suzuki-Trotter decomposition. And then each step is represented by a period of gates. Some of it is shown here on the screen. And so these gates, A theta, which is a 2-qubit gate, and some of the other gates are new gates. They're optimized 2-qubit gates, and they're now available as part of this Qiskit nature, they call it. So if you want to use these gates, they are optimized for quantum simulation of physical systems. I think our work either started it or catalyzed it, or our work of my colleagues. But now anyone can use it. It's called Qiskit nature, and nothing to do with a journal, just for physical world application. So, okay, the data from a quantum computer is always very anticlimactic. It's just these bars. So yeah, we wanted state psi plus, and we got it. It has the maximum probability. That's the quantum simulation, one number. What's the probability? But yeah, it works. So at least we can do braiding on the superconducting quantum computer, and maybe in the future also with actual Majoranas. But so far, no, we have not discovered Majoranas. It's important to talk about it. and also to learn how to be careful experimentalist or theorist, and how to, you don't have to trust the plot in the paper. You can ask for more data until it makes sense to you what they did. The methodological clarity has been achieved, that there is 2 hypotheses and there is a way to distinguish them with 3 terminal experiments. There is still challenges on the fabrication and materials side, and we have some ideas how to overcome them. So if we're successful, we should be able to establish these Majorana modes. And yeah, we'll keep you posted, and thanks for your attention. That's
great. Sergey, thanks a lot.
Yeah.
It's very, very exciting, very interesting. I think really from the lab. I see, unfortunately, no questions in the chat. Oh, there is one coming from Ranjit. Could you see the chat? Can you answer?
Yeah. Yes. So the question is, can we create entangled states from Majorana particles? So yes, we can. We haven't, but the scheme involves multiple pairs of Majorana, and then you shift them in a kind of a special way. First take this pair and exchange it, then take this pair and exchange it through. And then after a few of these things, you can entangle Majorana qubits. Yeah, so you can do full quantum computing with Majorana, and some of the gates are protected. So the second question is, are properties of nanowires dependent on temperature and stress? Yes, absolutely. We shouldn't be too sensitive to this in the sense that we always work at the lowest temperature possible. But certainly the properties of nanowires at room temperature will be different from the low temperature. And in particular, stress is a factor. For instance, sometimes we make a device and it explodes, right? It breaks from stress. So we need to control it. Well, that's a gross way to see it, if it completely dies from stress. But it can also influence it in more subtle ways, like you put metal on top of semiconductor and you strain it locally, and it can change band parameters, even spin orbit coupling, density, G factor. And this is usually ignored, not taken into account, but it maybe needs to be taken into account. Okay, and there's a question from Ilya. Could you explain about how the spectra produced by spin orbit coupling different from those induced by Zeeman splitting? Not sure what this question means. So I guess I can say this. Spin orbit coupling shifts spin states this way, and Zeeman splitting shifts them this way. So Zeeman splitting is momentum independent spin splitting. So the 2 parabolas for spin up and spin down just go one up, one down. And spin orbit splitting is a term like sigma cross k. So it is larger and larger with momentum. So what it amounts to is this. So you add to your energy dispersion, which is k squared, you add the linear k term. So if you have a parabola that has a linear term, it means the parabola minimum is shifted from 0. And one parabola is shifted right, and for the other spin, it's shifted left. Is this the level of answer that you're looking for, or anything, something deeper?
Ilya, I suppose.
Okay, so it's more detailed. We go to this slide. Now, which panel would you like to know about?
Ilya, I suppose you are also co-host, so you could use the microphone, can you?
Yes, I can. It's a bit unfair to those who can't, so I was typing. But yeah, just I wonder if you could explain a bit more how the picture I differs from picture C. So I understand that there is no superconducting gap there, but could you just explain how you get to the picture I again? Because I think that
I
didn't understand, and I think not really.
I think I can use this slide for this, right? So this is like picture C on the left. Well, I guess, well.
Okay, so this is picture C, and picture C is.
It's kind of like picture C, but also with superconductivity, but we have a magnetic field less than the gap. So you can see if magnetic field is 0, these 3 gaps are the same at Fermi momentum minus, at 0 Fermi, at 0 momentum, and at plus. These 3 gaps will be the same if this Zeeman energy is 0. That's just, and they're just equal to the superconducting gap. And then when we start applying magnetic field, we start closing the gaps. But we only closing actually the middle gap at k equals 0. We just start closing it because spin up and spin down split. Why don't we close gaps at finite momentum? That's because spin orbit field protects us. You can think of it as you already have a ginormous field in the spin orbit direction, and you apply a tiny field transverse to it, which is the external field. And so the total field doesn't change, and therefore this gap is not affected. It's kind of protected by spin orbit. So only the middle gap closes until at a certain point it closes completely. And that's when exactly the Zeeman energy is equal to the gap. So then a mysterious thing happens that it actually reopens. Well, it is not so mysterious because the reason why the gap was closing is because Zeeman energy was growing and the states were moving together, and then they just crossed through and kept going. And that's what we have on the right. However, the gaps at finite momentum minus k Fermi and plus k Fermi, they're still protected by spin orbit, so they change very little. Okay? So what we have as a result is that in the middle at k equals 0, the gap closed and reopened, while the other gaps stayed as they were. And so we inverted the bands. Is this helpful? Okay, yeah.
It looks like.
Yeah.
Okay, another question from Yulia Krasilnikova.
Okay, comments on topological superconductivity, how spin degree of freedom behaves here. Okay, so topological superconductivity is a spin triplet superconductivity. So that's very different from spin singlet, which is most superconductors like aluminum or lead, but also exotic ones like high TC, like YBCO. It is still all spin singlet. It's not spin triplet. Triplet superconductivity is peculiar. One of the practical properties is that it is sensitive to disorder much more. So in spin singlet superconductors, we have this thing known Anderson theorem. And Anderson theorem is tells us that scattering on non-magnetic impurities does not hurt superconductivity. So the gap remains the same, coherence length remains the same. So that means that we can have a pretty disordered material, like we can have an alloy, niobium titanium, an alloy, completely disordered material, and superconductivity can be very strong. And there is no such theorem for P-wave for triplet superconductors. Any disorder, magnetic or non-magnetic, destroys this superconductivity. That's why we also need extremely clean interfaces and crystals to see it. So there's another question. What do I think about induced superconductivity in the fractional quantum Hall effect? Recent paper of Philip Kim. I know that paper. So in terms of something superconducting coexisting with fractional quantum Hall effect, that part I believe. In terms of Cross-and wave reflection, the more exotic effects that people say, I do not believe. I'm sure there is another explanation, and the signals are not so clear. So, you know, you start in a good point, like you enter the fractional quantum Hall effect and you see something that is maybe superconducting, but then interpretation is not reliable. It is too far of a stretch.
All right, Sergey, I also want to ask you a question. You had this cartoon showing kind of crossover from age-localized majoranas to interacting Andreev states. And naively, one would wonder, I mean, for many condensed matter systems, there are cases where one can describe very same thing by different models. And I'm wondering if Majorana is just an idealization described in its own fashion of the Andreev states, which will be far separated. We all know that Andreev states will have non-local character, and I mean this has been all studied in various experiments. So what's your opinion of that? Is there a smoking gun where you really can distinguish the one model from another? I mean, in experiment, clearly you explained that you have this symmetry between left and right and so forth. But in general, are these models really so orthogonal to each other?
Right. So first of all, absolutely true that there could be other non-local states that have presence on both ends of the wire, right? For instance, the wires are pretty clean, like I said. Even though we want them cleaner, they're already clean. And so there could be just ballistic propagation of wave function from one end to the other. And there's some non-local effects, like I just mentioned, cross-and wave reflection, that are being studied, though, you know, I don't know, the evidence is also a bit shaky. I think the main difference here, what we are after, is this spinless character. So the wave functions I have on the screen are void of fermion doubling, right? So any Andreev state, you have actually two of them. So you can come in as spin up and reflect as a spin down hole, or you can come in and spin down and reflect as spin up. So there is these two Andreev processes, and if there's two, that's not the Majorana stuff. Or you can think of it as two copies of Majorana, and we want one, right? So this is the game we play in many different topological fields, you know, quantum hole, you know, quantum spin hole effect, and so we want this extra degeneracy lifted. And as far as distinguishing the hypotheses, yeah, so my method, these 5 criteria, is not smoking gun in a sense that there is no one graph that will tell you this is Majorana, right? It is kind of a comprehensive, a little bit tedious, but still within the same sample, within the same cool down, within the same experiment, by careful comparison to several things, you suppress doubt that it is something else. So I think of it as, you know, you have some promising evidence, but it is weak because there's a lot of explanations around it. And then you grow the evidence from the same wire, from the same cool down, and the evidence grows. And so the explanations around have to be more and more convoluted to explain everything that you've seen, right? And it will never be full, complete proof, but it will just be more reasonable that it's Majorana than not. And then at some point it will be pretty reasonable, right? And I mean, some things we observe are pretty non-controversial, like I mentioned, integer quantum Hall effect or superconductivity itself, right? If I did a poll and asked people, has superconductivity been observed? I'm sure I would get 100 yes and 0 no. Right? So eventually we get there by sort of careful work. And this kind of slow and maybe non-exciting path is what I'm advocating here, right? Sort of careful work, not a smoking gun.
Great, thanks a lot. Well, I think it was a great lecture, and we learned really from the front edge of ongoing discussions in the physics community about really hot topic which has been around for 10 years and still not it's not over. And Sergey, thanks a lot for your time and really being with us today. Really appreciate.
Yeah, thanks for sticking around for this. Yeah, and thanks for the questions, for your attention, and for invitation. I hope you have the good rest of the school.